Hi, I'm Dave Mueller, retired hydrologist from the U.S. Geological Survey and founder of Genesis Hydrotech. In this session, I'm going to describe how to prepare and open TRDI and SonTek ADCP measurements in QRevInt and discuss the system test, Compass PR, Temp Sal, and moving bed test tabs and the associated automated quality analysis and user interface that you can use to make appropriate changes. To begin, let's look at an actual TRDI measurement. In the previous session, I indicated that you only need to open the MMT file in QRevInt. While this is true, the MMT file is only part of the entire measurement. The MMT file is an XML formatted file that contains user-provided information, the system test, compass calibration, and evaluation, and the file names and paths to the actual raw data. The raw measured data are stored in the PD0 files. PD0 files are binary files and are not human readable. A measurement consists of one MMT file and multiple PD0 files, one for each moving bed test and one for each transect. So for QRevInt to load a measurement made using Wind River 2, the MMT file and PD0 files must be present. Wind River 2 may create other file types, but for QRevInt, only the MMT and PD0 files are needed. For data collected using River Surveyor Live, it is necessary to open the data files in River Surveyor Live and create MATLAB files. SonTek has not publicized the data format for their raw data files, and thus MATLAB files created by River Surveyor Live are the only SonTek files that the QRevInt can read. QRevInt can read the system test and compass calibration files, but those folders and associated files must be in the compass cal and system test subfolders for the measurement as shown here. So let's prepare a River Surveyor Live measurement for loading in QRevInt. First, we open River Surveyor Live and navigate to our measurement. We then load all the RIV and RIVR files from the transects only. We do not load the loop test. We open those files and we notice for this measurement we get a warning. The recorded file has missing samples. This is incomplete. Please download the complete file from the recorder for post-processing. We'll click OK. If you look closely, you will see there are two types of files, those with an R at the end and those without. Looking at 15 and 15R, we can see that 15R has the missing samples. Missing samples are typically due to a communication glitch between the laptop and the ADCP. In this case, it appears that only one sample is missing, but it is good practice that if an R file is missing samples, that you download the associated file from the ADCP, which is what this user did, and that is what this 15 file without an R is the file that has been downloaded from the ADCP. That's the file that we want to use in our final measurement. So let's remove the 15R file by clicking on that tab and then clicking X. We now have the data for the 4 transects that we want to use in our measurement. Before we make our MATLAB file, we have to load our moving bed test. In this measurement, there is a single loop test. By clicking on the icon, we scroll down and we pick that loop test and open it. We now have all the measured data associated with this measurement loaded into River Surveyor Live, and we're ready to make our MATLAB files. We click on the Processing Tools icon, and then the MATLAB icon, and then MATLAB Export All. And we get a message that all files are successfully exported. To check that the files were properly created, we can look in the Windows File Explorer window and see that the mat files for the 4 transects and the loop moving bed test have been created. To load those in QRevInt, we can open QRevInt, click on the Open Measurement icon. We select only the mat files for the 4 transects, not the loop moving bed test. QRevInt will automatically look for the loop tests or stationary tests, as well as the Compass Cal and System Test folders. Click Open, and we can see that the System Test has been loaded, the Compass Calibration has been loaded, and the Moving Bed Test has been loaded. Software, only one file is created. It's an RSQ MB for moving boat, and you can open that file in RSQ and follow a similar pattern to what we did with River Surveyor Live. We're going to open the file. And in this case, you see that you don't have to go through an extra step to open the loop or SMBA file. And in this particular measurement, they collected both a loop and a stationary moving bed test. So all the data are already loaded into RSQ with that single step. Now, to create the MATLAB files, we simply go to Export, MATLAB, and All. You'll notice it's created a separate folder labeled MATLAB. So we'll click OK, and then we'll go back and look at Windows File Explorer, and we see here's that folder that was created labeled MATLAB. And if we double click and look in that, we now see the MAT files for all the transects, the loop moving bed test, the stationary moving bed test, and it has also split out appropriate folders for the Compass Cal and Systems Test, which is exactly the format that is expected with QRevInt and is the same format as data would be produced with River Surveyor Live. Into QRevInt. Again, we select only the transects, and all of the data are successfully loaded in QRevInt. Now that we've successfully loaded data into QRevInt, let's begin by looking at the subtabs under the main tab. We can click on a row in the table at the top to show a different transect in the color contour and the ship track plot. We can also see a time series of the discharge, the extrapolation used, as well as some uncertainty estimate, and most importantly, the messages that have been automatically generated, and if appropriate, the comments that may have been inserted by the user. The Details tab provides us an assessment of the width, the area, the average boat speed, the course made good, the mean velocity computed as discharge over area, and the average water direction for each of the transects collected. In addition, the top line provides us the average width, the average area, the average boat speed, average mean velocity, and average water direction. The second line from the top compares the difference between the transects collected from left to right and those that were collected from right to left. We would expect in a good measurement to see very little difference caused by the direction of data collection. So in this case, we see only about a 2% difference in width, less than that for area, a very minimal difference in average boat speed. If everything were perfect, it would be 180 degrees in reciprocal transects, but as you move a boat back and forth, you're generally crabbing the boat slightly, so you never get 180 degrees exactly, so a 172 seems very reasonable. Very minimal change in the mean velocity depending on whether we were moving left or right. And again, very consistent water directions. Looking at the pre-measurement tab, we see that the site name, the site number, initials of the person collecting the data. In this case, there is no measurement number, so we could add one if we wanted to. We could also add a start, end, and mean stage. We can see that there was an ADCP test. It had 0 fails. There was a compass calibration. Because this is a SonTek measurement, there was no evaluation. They did a moving bed test, and there was a moving bed. They did not collect an independent temperature, or it's not recorded. The ADCP temperature was 14.8, a very small magnetic variation, and no heading offset. Looking at the Settings tab, we have the edge characteristics, both the left and the right distances, and we see that both in the left and the right edges were triangular. A consistent draft of just less than 5 centimeters. No excluded distance in this case. Depth is referenced to bottom track, and composite depths are turned on. The navigation reference is set to bottom track, but composite tracks are turned off. The extrapolation methods is a power fit with a custom determined exponent. Finally, the ADCP tab shows us the serial number, the manufacturer, model, firmware, and frequency. We can see that the depth cell size for this measurement ranged from 2 to 10 centimeters, and both the water mode and bottom mode are listed as variable because this particular instrument has an auto-adaptive mode for water and bottom tracking. Now that we've looked at all the subtabs of the main tab, let's begin to review our pre-measurement tasks. First, we'll begin to look at the system test. We can see that it is green, but let's take a look at what is under that tab. We have only one system test. In this case, we get the date timestamp, the number of tests, the number of fails, and if you were using a TRDI ADCP, you would also get a value under the PT3 test. For SonTek, the tests are fairly simple. You get a system test pass, you check the battery voltage, that the compass is working, and the temperature sensor is in working condition. For TRDI instruments, it's a much more comprehensive system test. Now let's look at the automated quality assessment for the system test. Good, or green, a system test has been completed with no failures reported. Caution, or yellow, means that at least one of the system tests have one or more failures. And if you're using a TRDI ADCP, it will also look at the PT3 test. The PT3 test indicates the potential for EMI. Lags 3 through 7 must be below 50% of lag 0, and lag 7 must be below 25% of lag 0. If either of these are not met, then a PT3 test caution will be flagged. Finally, a red warning will be created if there is no system test. Now let's examine the compass all PR system tests have at least one failure. I will come back to the data tab, but first let's look at the calibration and evaluation subtab. We see that the compass evaluation error is 0.2 run. Remember, SonTek ADCPs do not have a separate compass evaluation routine, but report the error from calibration as a measure of the goodness of fit to the calibration data. This is a different measure of error than that used by TRDI, so the compass calibrations are not comparable between manufacturers. Although the SonTek documentation suggests a good calibration should have a calibration error less than 0.5, experience has shown that a threshold value of 0.2 is better and is the value used to issue a caution in QRevInt. The calibration error for this measurement is just over this threshold at 0.21. Clicking on the Messages tab shows the quality check messages for the Compass PR tab. Note the message that the calibration result is greater than 0.2 degrees. There is also a message that one or more of the transects have a change in the magnetic field exceeding 2%. To explain that, let's go back to the Data subtab. All of the transect's names are highlighted in the caution color. Placing the cursor on the transect name shows a tooltip with the reason for the highlighting. During the calibration, the SonTek compasses record the strength of the magnetic field. During data collection, the strength of the magnetic field is compared to that from the calibration. If the magnetic field changes by more than 2%, QRevInt issues a caution. A change in the magnetic field indicates the potential for a condition different from the calibration, which could result in a heading error. Clicking on another row in the table will change the graphs immediately below the table. Looking at the graph immediately below the table, we see that the ADCP compass heading is the red line. The change in magnetic field is the black line, and a dashed black line indicates the 2% threshold for a change in magnetic field. Looking at this plot, we can see a significant change in the magnetic field at about 37 meters from the left bank. However, as we look at that change in the magnetic field, we do not see a substantial change, indicating that the change in magnetic field did not affect our compass heading in this case. What we do see is substantial change in heading throughout this transect. However, that change is due to the fact that heading is circular. So 0 and 360 are essentially the same value, and we're plotting this on a linear scale. So a change around 0 or 360 results in a change in the plot from 0 to 360 and appears to be a large change in heading when in fact it is a very small change in heading of just a few degrees. The graph at the bottom shows the time series of pitch and roll. The pitch and roll during the measurement should be within the pitch and roll experienced in the compass calibration of SonTek ADCPs. The graph at the bottom shows the time series of pitch and roll. The pitch and roll during the measurement should be within the pitch and roll experienced in the compass calibration of SonTek ADCPs. TRDI does not include limits for pitch and roll in their compass calibration algorithms. The checkboxes to the right of both plots allow the user to choose the variables plotted in the graphs. We could turn the pitch off or on. Likewise, we could turn the magnetic field on or off. Note that the external compass is grayed out or inactive. That is because there is no external compass heading such as that from a GPS compass available with this measurement. Focusing back on the table, we see checkboxes next to the transect names. A checkbox indicates that the transect is displayed in the graphs. By clicking other transects, we can change the display. If we right-click on a transect, we can add that transect to the display and display multiple transects. Single-clicking will restore just a single transect to the graph. Clicking in a table also allows the user to edit the magnetic variation, the heading offset, which is used only for external heading data, and the heading source. Clicking in these columns will open a dialog and allow the user to enter a value that can be applied to just the selected transect or to all transects. It is unusual that these settings would not be applied to all transects. Changing the magnetic variation should result in no change in discharge when using bottom track as a reference. So to illustrate the effect of a change in magnetic variation, let's change the navigation reference by clicking VTG in the toolbar. We see that the discharge has been updated with our new navigation reference, and we observe a slight directional bias in our discharges. So let's look at the magnetic variation and the effect that it may have. We know that a directional bias when referenced to GPS could be due to an incorrect magnetic variation. So let's try -1 degree and apply it to all transects. The result is that we have reduced our directional bias substantially, and it appears that -1 would be a better magnetic variation than -0.45. Clicking the heading offset does nothing because there is no external heading data. Clicking the heading source shows that the external heading is inactive. The internal heading is what we are currently using, and we do have an option to turn the heading off completely. Turning off the compass should only be used in very unusual situations where the compass is obviously in error, bottom track is used, and there is no moving bed. The colors, icons, and messages are based on these automatic quality checks. Inactive or gray, data loaded does not have valid heading data, such as from a StreamPro with no compass. Normal or black means the ADCP has a compass that was not calibrated, but the calibration is not required because neither a loop test nor a GPS are used. Good or green means that the compass calibration and evaluation were completed and passed the internal checks. Caution or yellow indicates that GPS data or the loop test are present, a compass calibration was completed, but there is no compass evaluation, or the evaluation exceeded the threshold, which is 0.2 for SonTek and 1 degree for TRDI. For SonTek only, a caution or yellow could occur if the change in magnetic field is greater than 2%, or if the mean pitch and roll is greater than 4 degrees, or the standard deviation of the pitch and roll is greater than 5 degrees. The warning or red will occur if GPS data or the loop test is present and there is no compass calibration, or the mean pitch or roll are greater than 8 degrees. Now let's look at the temperature salinity tab. The first thing you may notice is the time series graph of the water temperature as measured by the ADCP. The gaps in the graph indicate the time between transects. This graph allows the user to identify changes in the water temperature during a measurement. This example from another measurement shows that the measured water temperature changed. This is not likely due to a change in water temperature, but rather failure of the user to allow the ADCP to adequately equilibrate to the water temperature. This can happen when putting a cool ADCP in warm water or a warm ADCP in cold water. For this measurement, there is less than a 1 degree change in water temperature during the measurement. The next thing you may notice is the independent temperature has a caution color. That is because the user has not entered an independent temperature measurement as required by best practice policy. For TRDI measurements, it is possible to enter this independent water temperature in Wind River 2, and QRev will read that measurement. However, for SonTek, this capability does not exist and the user must enter the temperature in QRevInt. Let's enter 15.2 and apply. Notice that the caution now goes away because the independent water temperature is within 2 degrees of the ADCP temperature. Since the ADCP temperature was not manually entered, the comparison is made with the average ADCP water temperature. The quality checks used for temperature are: temperature range for the measurement is greater than 2 degrees C. There's a warning. If the temperature range for measurement is greater than 1 degree C, there is a caution. If a user does not provide an independent water temperature, as we saw in this measurement, there is a caution. If the difference between the user-supplied independent temperature and the ADCP temperature is greater than 2 degrees, there is also a warning. The table at the top allows the user to change some of the settings that affect the speed of sound. Remember, the Doppler equation depends on the speed of sound, and the speed of sound depends on the water temperature and salinity. QRev provides the user capability to manually set a temperature rather than use the temperature measured by the ADCP. To do this, we click in the temperature source column, and we can click User and enter a different temperature. We'll enter 16 degrees, apply to all transects, and you can see that the discharge changed just under 1% with our change in temperature. So let's set it back to the ADCP value. For measurements in saltwater or in estuarine conditions, the user can enter a salinity value or edit a salinity value previously entered in the manufacturer's software. It is also possible for the user to enter the speed of sound directly. And again, now we see almost a 7% change in discharge by changing the speed of sound. Let's look at the final tab in this pre-measurement assessment, the moving bed test tab. For this measurement, there are actually two moving bed tests, a loop test and a stationary test. It is likely that they did the stationary test when the loop test indicated some potential issues. The table displays the important characteristics of each test, the type of test, the duration, the distance moved upstream during the test, the moving bed speed, the moving bed direction, the flow speed, and the flow direction. The flow direction should be about 180 degrees different than the moving bed direction, as a moving bed shows that the boat would have moved upstream. The percent of invalid bottom track, and the compass error based on an assessment of the compass headings for the outgoing part of the loop and the return part of the loop, the percent of moving bed, and whether or not a moving bed is present, and finally a quality indicator. The automatically selected test by QRevInt has the file name bolded. For this measurement, the loop test is the test automatically selected for use by QRevInt. The procedure used by QRevInt to select a moving bed test is as follows. QRevInt will ignore any test that the user unchecks as valid. This gives the user the ability to tell QRevInt that something is wrong with the test and it should not be considered. If there are multiple tests, it will select the last valid loop test. If there are no valid loop tests, it will use all valid stationary tests. If only one stationary test has a moving bed, then a moving bed condition is deemed to be present. For the moving bed test, there are 3 layers of quality assessment. The first evaluates the quality of each test. The second evaluates the moving bed condition. And the third sets the good, caution, and warning colors, icons, and messages for the moving bed test results. For a loop test, the following criteria are used to determine if the test is good, has warnings, or has errors. A test with errors is an invalid test. The first criteria is the mean water velocity needs to be greater than 25 centimeters per second, or the status of the test is labeled as a warning. This is due to the fact that the user may not return to the exact same starting position, the compass may not be perfectly accurate, and thus at low velocities it is possible that random errors could result in a high percentage moving bed when in fact there is no moving bed. The second criteria is that the invalid bottom track should be less than 20%. If it's greater than 20%, the status is going to be an error, and an error means that the loop is not acceptable and cannot be used. The third check is an invalid bottom track is greater than 5%. And in this situation, we're just going to issue a warning and suggest that the user look at the data carefully because the loop test is highly dependent on the bottom track. The next test creates an error because if 9 seconds more than 9 seconds of consecutive invalid when they're making the turn at the far bank when it is absolutely critical that bottom track be maintained. The final potential error occurs if the difference in flow direction for the out and back portions of the loop is greater than 3 degrees and the potential compass error results in a discharge error greater than 5%, and the difference in flow direction is greater than the flow direction uncertainty. The presence of a moving bed from a loop test is then assessed using these rules. If the test is in error, the moving bed is unknown. If the closure error is not within plus or minus 45 degrees in the upstream direction, it is also determined that the test is not valid and the moving bed is unknown. If the moving bed test has either warnings or is good, then the moving bed percent is evaluated, and if it is greater than 1%, it is deemed to have a moving bed condition. A moving bed percent less than 1% would result in a no moving bed condition. And if the moving bed speed is less than 1.2 centimeters per second, again, it would be deemed that there is no moving bed condition present. For a stationary test, the following criteria are used to determine if the test is good, has warnings, or has errors. A test with errors is an invalid test. If there is no valid bottom track, the test has an error and is deemed invalid. If the duration of the test is less than 300 seconds, there is a warning. Duration is less than the recommended 5 minutes. If the last 30 seconds of a test has a coefficient of variation greater than 0.25 and the velocity standard deviation is greater than 0.03, the test is flagged with a warning. If the duration of the valid bottom track is less than or equal to 120 seconds, then the test is deemed to be invalid and an error is reported. If the percent of invalid bottom track is greater than 10%, then a warning is issued. The presence of a moving bed from a stationary test is then assessed using these rules. If the stationary test has errors, the status is unknown. If the percent moving bed is greater than or equal to 1%, there is a moving bed. If it's less than 1%, there is no moving bed. Finally, the overall assessment of the moving bed test is based on the following criteria. If it's a loop test, a caution or yellow color will be displayed if the mean water velocity is less than 25 centimeters per second, or invalid bottom track is greater than 5%, or the loop closure is greater than plus or minus 45 degrees, or a moving bed is present. For a loop test, a warning or red color is displayed if the invalid bottom track is greater than 20%, or consecutive invalid bottom tracks are greater than 9%, or inconsistent compass readings are identified. For stationary tests, a caution or yellow is displayed if the duration of the test is less than 300 seconds. There is an excessive coefficient of variation in the last 30 seconds. Invalid bottom track exceeds 10%. There are less than 3 tests present. A moving bed is present. Finally, a warning or red is displayed if there are no valid bottom track data. The duration of the test is less than 120 seconds. The messages from the final assessment are the only ones displayed in the main Messages tab. But clicking on the Messages subtab of the Moving Bed Test tab shows those messages displayed in the main Messages tab, in addition to the detailed messages for each of the moving bed tests. Now let's look at the options available to the user on the Moving Bed Test tab. As previously mentioned, the user could remove one of the tests by unchecking the checkbox in the User Valid column. When they do this, they will be prompted to enter a comment as to why that test was invalid. Something like, loop did not return to same starting position. The automatic algorithm will then select tests from those that are valid. In this case, it is only the stationary test. If we look back at the Messages tab, we'll see that we have now the comment that we just entered. The user could also uncheck Used for Correction. However, this is not the preferred option. It is preferred that the user uses the User Valid column to indicate that a moving bed test is valid or not. If GPS data were collected during the moving bed test, the GPS data can be used for the starting and stopping points of the test. This option can be useful when a loop test did not return to the same starting location, or the boat drifted substantially during a stationary test. Clicking the file name determines what is displayed in the graphs below, and the graphs are different for this loop and the stationary test. So if we click on this stationary test, we'll see that the graphs change, and there are now 3 graphs. A ship track plot, just like we saw previously with the loop test, but we get an additional ship track plot. This one is labeled as distance across the stream and distance upstream. So this is using the dot product approach we talked about when we discussed moving bed tests, and shows the actual movement in the upstream direction rather than in geographic coordinates. A third plot shows the moving bed speed, or the average moving bed speed over time, and this is where we would expect that an equilibrium condition should eventually be reached. And it appears that this test does a pretty good job of leveling out. The last 30 seconds is where the coefficient of variation is computed with the intent of determining whether an equilibrium condition has in fact been reached. Now that we've covered all the various features and tests in the Moving Bed Test tab, let's look at how we might use some of these features, both graphically and in the table, to evaluate our moving bed tests. Let's start with the loop test. And you'll notice we do have GPS data available for this particular test because the GGA and VTG are highlighted and not dimmed out or inactive. So we could take a look at how our bottom track compares to the GGA string, which provides position. But before we do, note that this black square, this marks the beginning of our test. So the test started here, they went across the stream, they came all the way back, and they finished here, which is in the upstream direction and results in a moving bed of about 2.4%. If we turn GGA on to look at positions, we can see things get a little unclear because of all the vectors. So let's turn our vectors off, and then let's zoom in and look at the starting and ending. And we'll see that the GPS started here. It actually shows that we finished slightly downstream of where we started. So we might expect a slight increase in our moving bed because we finished here rather than here, so the distance from here to here would be much greater. We can test that by going up to our table and say use GPS for test. And the result is, as we expected, a slight increase in our moving bed percent. So in this particular case, it's not huge. It's a percent or two. It would be up to the user to, based on their experience in the field, did they really come back to the starting point? Is this a GPS error? Although it is about 4 meters, but it could be due to multipath near the banks, if there's trees or something else near the bank. It would be up to the user to decide, did they come back to the exact same starting point, or should they in fact use GPS to determine the accuracy and the percent moving bed for this loop test. Let's turn things back, and now let's look at a stationary test. We look at our stationary test, and we can see that in fact the bottom track appears to have moved upstream steadily during our test. Again, we can turn on GGA to see how much the boat actually drifted during the test. And again, the vectors seem to be in our way, so we can turn the vectors off. We can once again zoom in on the bottom, and we can see that the test started here, and although we drifted around, the last point of the VTG is in fact here, and it really only moved about a foot. So we would expect if we went to GPS for this one, we would see a very small difference, but a slight reduction because we did drift upstream. And again, we saw a 1% reduction. Given this small movement, I would probably have ignored the GPS data here and just accepted the bottom track, but that is entirely up to the user. There is a 1 meter difference, and it does make a 1% difference in our moving bed percent. So that is where the user needs to be careful in the field, make observations in the field, and then compare it to the data when they post-process it in QRevInt to make a decision on what is the best reference for this moving bed test. That concludes all of the evaluation of the pre-measurement tests in QRevInt. And in the next sessions, we'll move on to looking at bottom track, GPS, depth, and water track.